Yeah, let's wait for 1:30 and then start.
Yeah. I think it's better.
All right, maybe we should begin. So it's my pleasure to introduce Mark Allen, and welcome back, everyone. So Mark is going to tell us about CDS services for reference astronomy data, supporting open science. Take it over, Mark.
Thanks very much. Mario. And thank you very much to Lewis and the organizing committee for asking me to give this presentation. It's a real pleasure, and happy anniversary to your data center there in Brazil. It's a real pleasure to be able to present to you about the CDS services. We really think of those services as being for reference data, for the data that you want to look up, that many astronomers want to use, and that are somehow connected to the referee publications of our discipline. And we have been here for some time in the CDS, and there's a strong culture of open science, making things freely available and open to everybody. And the presentation I'll give you today draws on the work of the CDS over many years, and also the team that's in place, so I acknowledge them. So CDS, it's a French acronym. It stands for Centre de Données Astronomiques de Strasbourg, the Strasbourg Astronomical Data Center, and we are hosted by the Observatory of Strasbourg and the University of Strasbourg, and the CNRS and the university are our kind of authorities. We are labeled as a research infrastructure, and we have about 30 FTEs of scientists, engineers, and documentalists that work as an integrated team here in Strasbourg. And you can see the historical observatory there in the picture, as well as one of our server racks. So CDS has been here since 1972. It has a mission which was defined very early on, actually, and it still resonates today. Our mission is to collect useful data on astronomical objects in electronic form. What other form is there these days? Improve them by critical evaluation, combining them together in certain ways, and importantly, to distribute the results to the international astronomical community. We're a French data center, but we have a mandate to serve the international astronomy research community. And to do that, we also engage in actually doing research on the data as well. We are, in order to run a data center like the CDS, we engage scientists who are active researchers, and indeed the whole enterprise is driven by science, and we have to evolve to meet the needs of the astronomy community. We're very much in line with open science, and of course the recent expression of that is through the FAIR principles, which are findable, accessible, interoperable, and reusable. And our services, they're all completely open. So this picture, generated quite recently, in some way kind of represents a lot of what we do. These pictures come from all of the catalogues that have been published in journals. So some 20,000 or so published catalogues that have, positions on the sky and information about astronomical sources in all different sorts of ways, published in ANA and published in the AAS journals. And with the systems we have today, we're able to sort of show you that all at once, with a density map of all of those catalogues, all of those different sorts of measurements, but linked to a position on the sky. And we can put that together using heel pit, using TAP, using different ways of accessing that very heterogeneous data published in all of those journal articles and by surveys and by missions and things like that. We're able to put those together as a density map on the sky and to sort of play around with it. And it sort of gives you a visualization, like that's all the data that's been published in journals for the last 50 years or so, and to see it, and it gives you a different view on the data that we hold in our repository. So the CDS services are ones I hope you know about, but let me tell you a little bit about each of the different ones. They have names: Sinbad, Vizier, and Aladdin, channeling the Arabian Nights. Sinbad is a reference database of astronomical objects, ones that have been studied in detail. So a paper that doesn't just give a name to an object or a catalog reference, but something that has measurements associated with it, a redshift, a color, a B magnitude, or something like that. And so Sinbad is the kind of link between astronomical objects published in the literature and some information about them. And so at the moment, there are about 12 million of those objects that have 41 million IDs, and they have 24 million citation links and some 15,000 acronyms. And that's the sort of data that people want to look up every day. You want to type your object in or the object reference that you have and understand where it is on the sky, as well as what citations, what papers did that information come from and which papers are about those objects. Vizier is our complementary service which deals with astronomical catalogues. And this again is drawn from the literature, where there are some 20,000 catalogues representing about 40,000 published tables. And if you add that all together, you end up with about 33 billion rows of catalogue data. So that's where it's complete, in a sense, compared to Sinbad, which is selected objects that have been studied, and Vizier is really the complete Gaia catalogue, the complete SDSS in terms of the numbers of rows, not the complete archive data set, but the reference representation of those catalogues that have been published in articles and are put into the Vizier service. And Aladdin is our visualization and image database, as well as applications like the Aladdin tool and Aladdin Light. And that's what's growing the most at the moment. We use something called these HIPS surveys that allows us to publish images and cubes. And that's where the data is growing the most for us. We have some 370 terabytes of data in the HIPS network that has a big node here at CDS. We also have a cross-match service, a portal, and the services are available through different APIs. And they're made interoperable through a very big investment in using, developing, defining the IVOA standards. So like the other data centers are participating in this meeting, we have relationships with others in the landscape of astronomy. And so we think of contributing to that astronomy infrastructure where there are missions and observatories that have their own archives, right? And then there are other data centers such as the ADS and NED and CADC we just heard about. A lot of those bodies participate in the definition of the virtual observatory, where we have European and French and international levels. We have a connection to some of the other infrastructures too. We are like Chenzu was mentioning about being certified through the Core Trust Seal and being members of these different organizations. I guess one of the things that distinguishes the CDS and one of our privileged relationships is with the journals, because we really process the data that is published in the journals, and the main ones are ANA and AAS journals and monthly notices, and about 30 other smaller journals. We have lots of users. We get some 2 million queries per day on our services from all around the world. And then also those observatories and the space agencies and the missions and the other data centers, they use some of our components like Sinbad, for name resolving, or Aladdin Light for visualization things. So our users are the researchers, but also the other data centers and also education and public outreach. So just a little bit of detail. I mean, Sinbad, just to give you some ideas of the numbers, there are about 13,000 papers published in astronomy every year, and we process those to update the Sinbad database, and that's done in a kind of supervised way. It's not all automatic. It's supervised by experts, but that's what allows you to then, put your favorite name in and get its position resolved. That's what we mean by name resolving. And Vizier is where we process about 1,200 catalogs out of those 13,000 papers per year. There are about 1,200 catalogs that are processed, bringing that heterogeneous data into the system by using a standardized metadata, and then making it available through all different sorts of interfaces, as well as putting DOIs on it as one of the most recent updates we've done. And so our users are able to access the data through web interfaces like this in different ways. So just a quick example of the interactive web interface. It's not the most used one now, but it gives me an opportunity to just sort of show, by having standardized metadata on top of these catalogs, it allows you to do things that you wouldn't be able to do otherwise, or are very difficult to do. So for example, here's just an example table that comes from Vizier, and in fact, if you make a query, you might end up with many tables that have say brightness measurements, flux measurements in different bands and different wavelengths. And across the catalog collection of some 20,000 catalogs, when you do that, you can actually, because of the standardized metadata we have for photometry, you can do a kind of sideways query across all of the data we have in Vizier, and you can extract things out that mean something scientifically, that you can start building SEDs, you can look at a photometry plot like this, because we've standardized the metadata from all of that information that was very diverse to begin with, and then becomes standardized in the system. And there's a service that does this called the Vizier Photometry Viewer. These services are fairly heavily queried, Vizier, for example, some 500,000 queries a day, and some 14,000 on the more sophisticated, detailed ADQL table access protocol queries there. I show this plot just to give you an idea of the fluctuations that happen. I mean, during the year, there can be many queries in 1 month through the interactive interface, but mainly through Python and through TopCat that uses the IVOA VO table standard. And so most of the queries come through that kind of channel. Those catalogs are also available in our fast catalog cross-matching service, which is interactive, but also available through a programmatic API that's available in AstroPy. And that's the sort of thing where the CDS services will be used in, for example, the Think broker for the Rubin alert streams. So I'm just touching on the different topics we have there. One of the places where we kind of integrate those services, Sinbad and Vizier, is in Aladdin, which is an image database in its own right, but is also a detailed application. And this plot is pretty busy, I suppose. I guess we're trying to show everything Aladdin can do all in one picture. So on the left-hand side, there's a data discovery tree that's built from a representation of the IVOA registry. So when you publish something in the registry, it can show up in the Aladdin data discovery tree. And you can use the keyword search at the bottom for that, for example, to find everything related to Gaia, including the Gaia catalog itself, but any other paper that's published something to do with Gaia. Then you can display it, of course, in these types of visualization. Behind that, there is image databases at CDS, but not only, also the ones that we access elsewhere. There's a sophisticated thing about how you manipulate that data with a kind of stack of loaded data sets you see on the right-hand side. And you can lock these views, you can make cutouts, you can run scripts, you can do all sorts of things in this fairly detailed desktop application for using data. But Aladdin's more than just the desktop, of course. There's the data, there's the clients, and there's the different services that are built on top of that. Aladdin Lite is our web viewer, and behind that, developed over about the last 10 years, are the technologies associated with what's called HIPS. So it's a HEAL-PICS representation of data that allows you to kind of do a lot of things. And it's really driving a lot of the innovations that we have at CDS and that we're taking out to the community. HIPS, what is it? It's hyper-hierarchical progressive surveys. It's based on HEAL-PICS. It means, this thing that we're very familiar with, the more you zoom, the more you see. By doing it in a very scientific way, using FITS files behind, you can preserve the dynamic range of the data. You can do scientific things as well as visualization things. For example, what falls out of this? Well, falls, I mean, you can have an expert engineer to develop a system that makes cutouts from any of those 900, all-sky surveys that are published in the system. That's called HIPS to FITS. If you haven't seen that before, look it up. There's an indexing system behind it based on HEAL-PICS and the way of putting it into tiles and pixels. And again, it's this idea of heterogeneous data in a homogeneous system, whereby the WMAP image of the cosmic microwave background can be described and used in the same image, the same system as the 25 milliarc second pixels that you have from, for example, the HST ACS cameras. And that's been standardized at IVOA. You can find the IVOA standards here. You can look them up in ADS. They're in fair sharing. The standards themselves have DOIs, which can be cited and referenced. So here's what that enables. You have the Pan-STARRS data. You zoom in. You are starting to access different orders of HEAL-PICS in this multi-resolution representation of the data. Those data have a lot of diversity. If you look at the different HIPS that are published across the different wave bands, so you publish with a different resolution, and you can see from gamma rays to radio that this system encompasses many different types of data. And you can see also, because HIPS is not just for all sky data, you can put a pointed survey in there. You have all these all sky surveys that cover the full 4 pi of the sky. But it's more than that, because we have pointed observations too. There's representation of the whole HST imaging archive in HIPS as well as some of these other missions like Chandra and XMM. And it's just very interesting to start seeing what data is really there in terms of sky fraction, in terms of resolution that's used. In Aladdin desktop itself, we update things to enable the users to do different things. So we've had kind of evolution with wavelength over the years, and now we're implementing time in the services of the CDS. So the same system that HIPS is built on allows a kind of coverage map of the sky, which is called the multi-order coverage map. And that's being extended now so that you can have a kind of time multi-order coverage map. And this little barcode that you see on the right-hand side is a representation of the time coverage of a survey. But you could have the time coverage of a mission, of an observation, of a catalog, of an event, and oops, I'm going the wrong way now. Zoot. Sorry about that. You can have a time representation of that, and you can use these coverages in a way where you can say, give me the survey that intersects in space and time with this event or this other catalog. And so that's proving to be really useful. So search for space and time across the collection. HIPS is not just CDS, but it's a system which uses this IVOA standard, and there are a number of nodes around the world, and this is kind of getting a life of its own with all of these different nodes that are available, where you can mirror the HIPS so that it goes faster to your country. If you have a HIPS node there are new nodes coming all of the time. It's a distributed system, and you basically declare you just go and do it, and you declare it in the HIPS list, and it becomes part of the IVOA registry. It's growing very fast. There are about 900 of these now, with about 370 terabytes in the system. And the tools for using them are also, they have their own life as well. I mean, there's tools which use LIneA, like ESA Sky, like the eScience Archive, like the Datasets and SkyMapper. But then there are other applications which also just use the fact that this is an open system and connect in. So MISAR, Stellarium, Firefly, the Worldwide Telescope, Digistar version 7, they use this HIPS network of imaging data for their own purposes. At CDS, we developed the LIneA widget that you can embed in your web page to access this data. So some of the data centers might be interested in knowing that there's a WebGL version of this, which is in the pipeline, that allows some more powerful image visualization aspects of that, and it's supported by the ESCAPE project and should be released later this year. It allows you to do things like render a million source catalog in a very, in real time on top of your images, and change the sky, change the grayscale, change the color map, and there's this very sophisticated way of doing that. And also what it enables is the different projections on the sky to be used, whereas the LIneA was using just one projection. With the new system, you should be able to use the different projections and have a lot more flexibility in that. So those services which are available through the CDS, we are also responding to the users' preferences and needs, where there's a big demand for using these types of services in notebooks. And so IPAC Aladdin is the version of Aladdin which can be used in Python notebooks. And this is something that's growing quite fast. It's very popular with the new young users who are coming and wanting to be able to access these services alongside of those others that are available through Python. And indeed, many of the presentations at this workshop are about science platforms, and we're thinking a lot about that. So the kind of approach that we're developing to science platforms in terms of CDS services is just, on one hand, to make sure that those data are available through the platform, like you've just seen in the example, to contribute components like Aladdin Lite and IPAC Aladdin and Simbad to do name resolving in your science platform, or in your, when you want to deal with that data. We do have a number of services that, of course, fit very cleanly into this kind of computing next to the data. The CDS cross-match service is our kind of example of that, where a fairly heavy computation can be done locally here on the data, and the results can be provided to the user. And there are other examples, for example, computations on HIPS, where we can generate SEDs, or we can make cutouts with HIPS to fits. So one of the test beds that's relevant to us in terms of the science platforms is the one that's being developed by the ESCAPE project that was described briefly yesterday by Ian. We have questions like, can we put HIPS nodes in the data lake and make use of those distributed systems? And we're thinking very strongly about how we use EOSC, the European Open Science Cloud resources, for hosting those sorts of notebooks. So coming up to the end, putting down some of the challenges that face us as a data center in the era of big data. There's kind of two ways that things are growing from our point of view. So one is there are more papers being published in astronomy. So every year there are more papers, we process them for our services. And of course, that's, each table is on average bigger and wider and more complex. And so our response to that is to become smarter about it, to make it the tools that we use internally to process the papers more efficient, and to also acknowledge that this is not an automatic process and that we have expert data stewards, our documentalists, our engineers and astronomers who help supervise that work. And we are faced with how do we make use of all of the developments in machine learning and AI to make that better. And then a different type of growth is the exploding data volume. When there's maybe 10 or 15% more papers per year, on average we need to increase our staff by some almost linear fraction. Whereas when the data doubles, fortunately we don't need to double the amount of people working on that, but we have our systems which use a hierarchical way, such as HIPS, right? We have this hierarchical approach to the big data. And with all of these very large data sets coming, we are at the CDS. We are not the archive. We are not the processing data center. We have to ask ourselves the question: what is the reference data relevant to CDS that we should include in our services? So at the moment, we do have the largest catalogs. We do have the 2 billion source Gaia catalog, and we look ahead to the tens of billions of source catalog that will be on the timescale of 2025 or so, like that. Of course, when you multiply that by 800 time epochs, that looks a lot more challenging, although not kind of impossible. In terms of the imaging data, we have the Pan-STARRS data, which has 15 terabytes per band in HIPS. And when we look at Euclid, then that's kind of approachable in terms of an annual data release or a specific per band data set. But when you get into petabyte scale HIPSs or petabyte catalogs, that requires us to really think differently in terms of what sort of change in scale of something like CDS needs to come in the future. So our approach there is to be involved in projects like ESCAPE, where we have the development of data lakes. We have also the connections to the French national data centers, even locally at the University of Strasbourg, who have implemented a 140 rack data center just a few hundred meters away from the CDS. On the other hand, we have designed things to be scalable and distributable, and we've done that with HIPS, and I think we should do some of those things together with the virtual observatory. And just to finish, there's different types of users. It's very fun to address the very young ones, as well as the public outreach, where we can combine historical things such as what we have at the Observatory of Strasbourg with an interactive display of the data available in the virtual observatory through HIPS. And with that, Mario, I'll finish. Thank you for listening.
Thank you, Mark. This is a really excellent overview of everything that's going on in Strasbourg. We have a couple of questions. JJ Calvert asks, is the cross-match service deployable outside the CDS? I.e., could other TAP services use the CDS cross-match locally, or is the cross-match only at CDS and the data from a TAP service must travel to CDS for the cross-match to happen?
Yeah, that's the way it is at the moment. If you're going to upload, I mean, the crossmatch allows you to crossmatch any of those 20,000 tables that are in Vizier. Of course, you can upload your own table and then cross-match it against any of those. But of course, then you can end up with a very large result that you have to download. And yeah, that's a bottleneck. That's something that we get asked a lot. The cross-match service is available, for example, through TopCat, but there you're limited, of course, because you're not going to upload a Gaia equivalent catalog through that system to then cross-match at CDS. So it's something that's in development to bring the cross-match service a little bit more in line with the TAP services, but it's not there yet. It's not there yet. So it's a separate special system, but can do very, very fast cross-matches. It'll be relevant to the LSST brokers, and we're connected a little bit with the one in France called Fink. And we're happy to discuss also how those services might be and that big investment that we made in making those cross-match services can be used in platforms and with other systems.
And then Knut Olsen asks, can you tell from, for example, from Python queries, or which queries come from automated scripts and which queries come from interactive work? So just wondering about the fraction of users who are working interactively versus automated script usage.
It depends on the service, but I would. I mean, it's really dominated. It's really dominated by those Python queries these days. I hesitate to say that it's about 80% on the sort of scripted API type queries compared to the interactive web pages. So you enable the access to Vizier through TopCat. That happened about 10 years ago, and the usage really exploded. And now with Astro Query and with different types of APIs, that really gets used a lot. Yeah.
All right. Thank you, Mark. There are actually 3 more questions in the Google Doc that I hope we can answer there, but we have to move on to Vandana. So thank you once again, Mark. And
You're welcome.
Vandana, if you can share your screen. Okay, so next we have Vandana Desai from IPAC talking about enabling next generation science investigations with the NASA Astrophysics Archives.
Thank you. So as Mario said, my name is Vandana Desai, and I'm the science lead for the NASA IPAC Infrared Science Archive, but I really want to emphasize that this talk is going to have a broader scope and has developed over a lot of conversations with Tess Jaffe and Alan Smale from HESARC and Eva Momcheva and Josh Peak from MAST. And so this has really been a joint effort amongst these 3 NASA Astrophysics Archives. So in order to really talk about the future, it's important to say where we are right now. So the NASA Astrophysics Archives are distributed roughly via...
Vandana, there seems to be a problem with your slides. We're only seeing a black screen.
Oh, let me try not going... Does that help?
That works. We can see that.
So for some reason it's not going. It doesn't want me to go full screen. Okay. Okay. So the NASA Astrophysics Archives are distributed roughly along wavelength. So HESARC is the high energy archive. URSA is the infrared science archive, and MAST is the UV and optical archive. Now, these are sort of blurry definitions. They're not, we don't stay exactly in our boxes as they were originally envisioned. But it's important to remember that these 3 archives have historically operated really completely independently. We all get reviewed by NASA, but our budgets are separate. We use different databases, we use different technologies, we make our own decisions, and that there's been increasing collaborations amongst these archives in recent years with the advent of the NASA Astronomical Virtual Observatories, which coordinates the VO uptake amongst these three archives, but implementation is still separate. For the first time, I'm going to tell you about probably our first project that is just in the beginning stages that represent us working together. Okay, I have to figure out how to, okay, there we go. Okay, so one of the things when you're thinking about looking to the future is what is working now? So is our current system effective? So this is a plot that we show a lot when we do group presentations like this. And it's looking at the fraction of papers that use archival data from the great observatories. So each of, we have a high energy great observatory, a UV optical one and an infrared one, Chandra, Hubble, and Spitzer. And we find if you analyze the publications that the fraction of papers that use archival data from these missions, meaning that none of the people who wrote the paper were on the proposal to get the data, that fraction, as years go on, ends up being quite high. And so most of the papers written with data from these great observatories are archival in nature. And so Josh Peak wrote a white paper on that for the recent decadal survey called Robust Archives Maximize Scientific Accessibility. So the question posed at the top of the slide is the current system effective? By this metric, it would seem that archives are a good investment, given the cost of the missions, as Alex mentioned yesterday. The cost of the archives is much smaller and really does pay off. Okay, so what can we attribute the success of the NASA Astrophysics Archives? Well, first, you can't ignore the fact that very high quality data is going to be used by the community. I mean, they will find a way to use it. And I want to point out that this doesn't just include the mission data that I just highlighted, but also contributed data. So we find when we analyze the publication statistics that the data that users enhance and contribute back to the archive get used even more than the pipeline reduced data. And so this has been a really important aspect of the archives, accepting contributed data from Hubble and Spitzer and Herschel and even now WISE. And second is the NASA's commitment to long-term archives. So IRAS was the first data archived at IPAC, which is the home institution of ERSA and NED and Exoplanet Archive. And that was back in 1985. We're still serving IRAS data. NASA still pays us to serve IRAS data, and it is in their, it's in the culture of NASA to preserve that data forever. And forever is a big word. And then I think something that is very important and should not be overlooked is that the archive workforce is really essential to the science impact of NASA missions. And so this is a quote from the Portals to the Universe NRC report. And it said, successful research using archival data sets is dependent on the resident expertise and corporate memory that reside at the science centers. And so it's not just scientists that do active research, but also scientists that really understand the data sets very thoroughly and can provide user support when the documentation, we'd like to have good documentation, but often users have questions even beyond that, and archives sort of inherit that expertise. When they inherit the data, we usually try to hire someone from the mission so that we can help users use the data. And then that brings me to the second bullet point there, which is that we enjoy a tight connection between projects and archives at all three of these institutions. So you can transfer knowledge, you can really get at the use cases, you have a really intimate knowledge of the data. And then finally, of course, we have many tools for discovery, exploration, and analysis that's really critical to making the data not just available, but really usable. Okay, so if we think that we're doing, we're seeing papers come out, there's a lot of papers that use the data. So why do we want to change? What is driving this change? So this is a plot that was from a white paper that a lot of people who were attending or associated with this conference were also on, which shows the data volume over time for selected astronomy missions. And so, the trend you can see is going up. This plot was made in 2019. That's why there's the vertical line there with sort of extrapolations to the future. But we're definitely entering the petabyte scale. I know yesterday people were talking about the exabyte scale. We are, I think, at this transition that Alex was talking about between, smaller data sets and really going into the big survey data that won't be surpassed for some time, and that we really need to help people use better. So on the left is sort of a very NASA-centric view of this. So if we look ahead to 2030, which is an exercise that we are doing with headquarters right now to figure out our path to the future, we're going to see that, Euclid may be complete, SphereX will be complete, JWST will be towards its end, Roman will be near its end, the NEO surveillance mission will still be operating, but all of the NASA legacy data will still be in use. So I very much agree with that. You see it in all of the statistics that we can find, that the publications continue long after the data stop being taken. And then we expect there will be some missions in development, and we don't know what they will be, maybe a probe or a flagship. But with the trend that we see here, we can guess that it's probably going to be continuing in this trend. And then, of course, although we're NASA-centric, you really can't think about the future without thinking about Rubin, which will be at the, near the tail end of its 10-year nominal mission, or survey, I should say. Okay. So in addition to just the volume of data, I think it's really important also to think about, because that's really dominated by images, and images definitely are used in many science use cases, but catalogs and spectra are sort of like higher level products that people are often the starting point. And so now here I'm going to be talking more about URSA instead of all of the archives, just because I know it better. So at URSA, the challenge that we have is we have a lot of tables from large area and all sky surveys, and they're very long. So we have 10 billion to 10 billion row tables, and several tables that are greater than 10 billion rows. And our largest table from the NEOI's reactivation mission is over 130 billion rows. Part of this is that NEOI's keeps getting extended, and so we keep jamming larger and larger tables into a database solution that wasn't designed to grow this large. And so we're making it work, but it's limping along, and that's going to be one area where, if this mission ever ends, we can retool the way that we're handling the data. But this is one of the challenges. How do you modernize while you're still actively trying to operate, ingesting data continuously? So Spectra is another area where we already have data sets from Spitzer, Herschel, SOFIA, and IRTF. But they're small, they're sort of manageable, they're not really survey mode, they're more like custom pointed observatories. But the next years are going to see SphereX coming online, which will produce 1 billion galaxy spectra, 100 million stellar spectra, hundreds of thousands of ice absorption spectra, a million, that's not a mission quasar spectra, it's 1 million quasar spectra, and asteroid spectra too. And then Euclid, so URSA will be archiving Euclid data as well as ESAC, and that's going to provide 30 million galaxy spectra. So this is going to be a regime, like an area of growth for visualization, for serving data through protocols that are useful. We have the simple spectral access VO protocol, but it's really designed for one spectrum at a time, and doesn't seem likely that that's how users will be using these data in the future. Okay, and simulation. So this is an area that we're also expanding out into. We know that cosmological simulations are necessary to achieve the science goals from individual surveys like Euclid, Roman, and Rubin. but also they're very critical for achieving science gains from jointly processing those data sets. And so it would seem natural to have coordination between these agencies. So NASA has some interest in Euclid, but the DOE and NSF have interest in Rubin and Roman. So these separate agencies need to coordinate. It's challenging right now. The way the money flows is difficult, but NASA has taken a specific interest in the archiving aspect. And so there's a sort of like a pilot project to investigate how we would need to evolve in order to better serve simulation data. And so the first thing we've done is ingest and serve the LSST Data Challenge 2 cosmological simulation. So it's available through our observational tools, which needed some tweaking because there are some contextual things that don't make sense for simulations. And of course, it's available through Python notebooks through the usual virtual observatory protocols. Okay, so in addition to the volume of images, catalogs, spectra, and simulations, we also have small complex data sets. So NASA has renewed interest in these smaller missions. We've just been asked to scope out what it would take for us to increasingly serve data from CubeSats and the New Pioneers program and balloons. Next year, the Gusto mission, which is a balloon, will be launching and we'll be serving data from that, but we expect this segment to grow. Okay, so what will people be doing with these data sets in 2030? So this has been talked about already in this meeting. The rise of machine learning. People are going to be using more sophisticated statistical analyses. They're going to be jointly analyzing data. We're very far from the time where I'm an optical astronomer or an infrared astronomer, an X-ray astronomer. There's still a little bit of legacy of that, but people are no longer seeing it that way. Astronomers are multi-wavelength astronomers. And you used to say you're a theoretical astronomer or an observational astronomer. Well, many observers have now to deal with simulations because you just can't interpret the data or even create analysis tools for the observational data without consulting the simulations. And in this part, the last bullet I think is really important, and I think JJ hit on this a little bit, that people are still going to need legacy code. There's still, there's Spitzer code that was written for those cubes is really hard to reproduce, but it's going to become obsolete even when perhaps the data are not obsolete. And so things like containers can help keep the code alive. It's not just about keeping the data alive, but there's information and labor in that code that is really valuable to preserve. Okay, so there's also a sociological aspect to taking these steps to evolve the archive. So the first one I want to point out is inclusion. So NASA has added inclusion to its elements of mission success. I'm going to talk about that a little bit more in the next slide in particular. But so I'll go into collaboration. So what do users expect? They expect to be able to collaborate. So, this joint editing of Python notebooks, for instance, that was brought up earlier. But, the examples of Google Drive, Overleaf, Slack, these are tools that we use to collaborate, and it sort of permeates, that expectation permeates astronomers, every tool that we want to use. I want to bring up the user contributions again. We're understanding the value of people putting their, insight into enhanced data products and their expertise into enhanced data products, and then also to open source software, where there's been a real reluctance to rely on open source software because we don't know, you have a big mission and, it's very tightly controlled, and having something be open source is kind of scary to rely on from a mission point of view. But this is something that's changing in the community, and I think that there's a place for it in the archives, especially as we hear again and again this talk about science platforms. And then there seems to be a greater willingness to learn and borrow from industry and also from the greater research community. So, at NASA Astrophysics, we're also thinking about what is planetary doing? What is Earth science doing? Earth science has much bigger data sets. Planetary has a different approach to organizing their archives and dealing with standards. and so those are things we can learn from. So I want to go back to the idea of inclusion, which I think involves meeting the users where they are. So that requires understanding who are your users, and this is partly it's not like who are they current. It's partially who are they currently, and it's also who does NASA need us to serve. So when so the answer for us at the NASA Astrophysics Archives is we are supposed to serve tools and data for amateur astronomers, undergraduates, graduate students, postdocs, professors, staff scientists, and citizen scientists. That is very challenging. The VO makes it possible to build sort of bespoke tools for all of those, and but it's very hard to make one tool that effectively serves all of these people. Meeting users where they are also requires, I think, talking to users. We do have a user panel. Each of the archives has a user panel that's supposed to represent the community. It's roughly 7 or 10 people that rotate through that give us input on what we are doing, what we should be doing. And we also conduct user surveys. So I thought I put down some of the responses from our most recent user survey because I think that they're instructive. So most respondents didn't know what an API is, or they believe, or they said that they've never used an API. I mean, the vast majority, that this was just a word they don't know. It's not in their vocabulary. Most respondents have heard of the virtual observatory, but they report that they have never used it. They probably have, but they don't know it. And in fact, there is sort of a stigma associated with the virtual observatory in the minds of many astronomers, at least in the US, which is something that I think is an education thing. Most respondents are comfortable with Python, but there's a sizable fraction who still use IDL, like 40%. It's a big fraction. When we did our programmatic review with NASA recently, and everyone was jumping on the Python bandwagon, and we were sort of assuming that it was, it has such strong uptake in the astronomical community, but of course our reviewers tend to be more senior, and they said, do not take away my current modes of access to the data. Do not replace my GUIs with Python. Don't make it impossible for me to continue to use IDL. So we get pushback on that from certain segments of our user base. We asked users what are their top 3 challenges, not just with using data from our archive, but just in general. When you do your work, what's hard for you? And their number 1 response was documentation. It's hard for them to find documentation that they need in order to understand the data sufficiently to do their science. So yesterday there was some talk about how we could have the machines go in and read the papers and get out the column headings, and you could just do ingestion automatically like that. I mean, I think, perhaps I underestimate the machines, but I think that I'll believe it when I see it, if that is actually good enough to do science on. The second most biggest difficulty they had was just finding which data set would suit their needs. So data discovery, there's so many data sets now, it's only growing. It's like what Google did well was give you not just a list of everything that was related to your search terms, but the good results, the ones that would be most useful. And I think that's something that we could improve on. And then, third was download time. We keep talking about the volume of data sets, but I think it's important to remember that there are barriers in front of that. Okay, and then we asked about the concept of science platforms, like logging into a system that helps you do your science, where maybe you're doing your analysis on data that is remote. And the biggest concern about that was a learning curve. They just thought, that's different, it's going to be hard. Okay, so going more into the science platforms, we've talked about it a lot already at this conference, so I'm not going to rehash it, but there's just a table here of some science platforms that are in development. And HESARC and IPAC and MAST all had their own science platform in development, and they were separate, 3 separate rows on this particular table. And when we did our review with NASA, they told us that having the archives collaborate on a single unified science platform under unified funding is a more likely path to true interoperability. So that is what we will do, pending approval and plans and funding and all of that. So none of this is set in stone. This is under discussion right now. But even if we collapse 3 of these rows into one, it still is obvious that we cannot have all of the data that an astronomer might want to use under a single unified science platform, at least not co-located in some way. And then the other challenge here is that we need to build this new system while we continue operations and still meeting our deadlines for releases of ongoing missions, which is our, we can't let the bits fall on the ground from those missions. That would be catastrophic. So what are our ideas for this future unified science platform? Again, preliminary. So there's 3 essential components. There would be a cloud-based interface and a supporting system that would make heavy use of open source research software developed in other areas of science. There would be a nice collection of notebooks and software containers that would help people carry out multi-wavelength and big data science. And this is where we're capturing expertise and sharing the expertise to bring people up to speed as part of meeting astronomers where they are. And then third is that we really need to think about our data services. We need to make them location agnostic. We are not going to be able to afford to put all of the NASA Astrophysics Archive holdings in the cloud at this time. Maybe that will be feasible in the future. So our data services need to not care where the data are, and that needs to be transparent for users. And it needs to not just be NASA archives, but we don't want there to be barriers to data that are not held by NASA. Okay, so a little bit more on each of those. For the cloud-based system that is rooted in open source research software, our starting point is to borrow from existing systems such as Pangeo that combine Jupyter frameworks and open source systems for the cloud. This system will be built as code on the cloud, and it'll provide a place where the member archives can work together. This will be the first time that we actually have like a shared development platform. So that will be something new. We'll be combining teams in a new way. And then hopefully, this system is something that anybody sufficiently motivated could redeploy if they needed to. If, for instance, we were unable to provide the cloud computing or other features that people wanted, they could potentially add their own. So for the notebooks and software containers that would really be the content of this system, few users are really well versed in the software tools at other wavelengths than that maybe they were trained for in graduate school, or know how to scale up their data or work in the big data regime. And so these notebooks will be really useful for teaching novices quickly, and that's really important to really get uptake of this system. And then again, I don't know if any of you have tried to install legacy data. I have literally given up on projects because I just couldn't get the software that was necessary to work, and I did not have time to rewrite the software. Keeping that going is just really critical for keeping older data sets alive. And then for the data services and how they need to evolve. So I think JJ was talking about this a little, and I think it's interesting. So we want to bring the compute to the data, the software to the data. But we currently know that our data is not all going to be able to be in one place, not for the NASA Astrophysics Archives, not at this time. So we're going to be able to bring some of it to the cloud. We'll have to be very judicious in how we decide what to do. There's going to be, a science curation aspect to that, as well as the engineering work required to do that. But we can also build, like JJ was talking about the SOTA service. We can anticipate some things that users need and just make the pipe that comes back to them small. Like they ask for a big compute, they can send that request off through a small pipe. It happens somewhere. It could be in the cloud, it could be on premises, and then a small answer comes back. The difficulty and the pushback that we've gotten with this from users is there is some concern about who is making the science decisions. These need to be, these APIs that do higher level things. People are concerned that the archives or the data service providers would be making science decisions that people want to make for themselves. So that is something that we need to be aware of. And then NAVO, which I already mentioned, is going to have to work with the IVOA to identify future use cases where existing protocols don't meet user needs. I asked that question of other people and got some interesting answers. And in our case, we know that probably the spectral data model and APIs for dealing with spectra are going to be an area where we are going to see evolution. Okay, so I think I'm doing pretty well on time, amazingly. The summary is very high level. We want to keep what works. We are envisioning a science platform that could be designed to enable science from distributed NASA astrophysics data centers. But all of what I just said is very preliminary. It's important that I say that. But as we build it, we want to make sure that we meet users where they are and serve the entire community, not just the so-called power users. And that there are many challenges with this, but one of the big challenges is building something new while continuing to operate an active data centers that are working with new missions, ingesting and serving data from existing missions, and preserving and maintaining and keeping up to date old missions. So that's all I have. Any questions?
Thank you, Vandana. This is great. We do have a number of questions for you. First comes from Robert Nikita asking, regarding databases that outgrow their original design goals, do you evaluate other or newer database technologies when that happens, or do you use new technologies only for new missions?
So well, it's a very complicated, we use many database technologies right now. We use Postgres and Oracle, and we just got all of our stuff out of Informix. And usually when a mission ends, there's a closeout period. And at that time, we can ask NASA for funds that would be needed to transition a mission into a long-term archive. So for instance, NEOWISE was supposed to close out like many times. And each time we told them, well, when it closes out, we're gonna put in an entire new data, we're gonna redo the database. But then they tell us, oh, by the way, this was supposed to be your last release, but now it's not. And so we can do it whenever we want. We have to make a proposal for it. It's just that for us, with the staff that we have, it's difficult to transition while we're taking data every day. So for NEOWISE, our overguide said that we would investigate new database technologies and perhaps move to a new one. So that happened at mission close, but if that did happen, we would also use the new one for other future missions where it made sense, like for instance, ZTF.
All right, let's try to get through a couple more questions. So JJ comments that when keeping the code alive via container, we also need to keep the documentation alive. We have examples of code that we can run in the VM environment, but the documentation of that code is mostly lost, assuming it actually existed in the first place.
Yes, absolutely agree. We harass missions for documentation. It's actually a requirement when they give us data or software.
There's a question from Dino Bektesic. Is your user survey report available somewhere? And is there a newer version of the survey that, or are you planning a newer version sometime in the future? Yes,
so we have it available on our website. I can put the link in the chat in a minute. And yes, we do them periodically. When I send you the link, you'll see they happen periodically. We try to do them before big programmatic reviews. So the way we're funded is that every 4 to 5 years, we write a proposal for the next 4 to 5 years. And in preparation for that, we do a user survey to doing our due diligence to make sure that we are going in the direction that the community wants.
Yeah, the 40% number about IDL, I think, was eye-opening, especially for a number of us who are kind of working in Python land and tend to forget that not everyone is the same.
Well, there are people who do IDL and Python, so it didn't like add up to 100.
Yeah.
Yeah.
Robert asks, what do you think it will take for all data centers to throw their monies together and put all of our data into a common data lake where we can access it and stand up various science platforms and archives on top of it?
Right now, I feel that it's so hard that I don't think it'll happen on the timescale that is interesting. Funding barriers are real. Like, we are trying to work in this tri-agency arena, and everybody wants to work together, but it's hard. It's just the system at a higher level than us isn't necessarily set up that way. I think that for now, it's better to assume that we can't. And especially, that's only with 3 organizations in the same country. And then you expand that to different countries. And I am very pleased that we are finally, I know Europe has been really great about their uptake of the IVOA, for instance, VO standards, but we're we're not even there yet. So, well, we're getting there. We're making good progress, but I think it's too big of an ask right now.
Right, 2 more questions and then we'll move on. One from Bruno Altieri. Is the initiative of a joint survey processing of Euclid Rubin and Roman at pixel level envisaged on this unified science platform?
No, so these are actually parallel but communicative efforts. So we don't envision this science platform. We're not building this to solve that problem. There are so many more that's a very important problem, but there are so many science cases that aren't that problem. And so we don't want that one to dominate over all of the others. So we will probably be sharing technologies and together coming on a convergence of how these can be compatible, but we haven't crystallized those ideas yet. And
the final question we have time for, with apologies to all the other questioners. So JJ also mentions for the SOTA actions, CADC has had the same question: who's making the science choice? We're currently only providing decision-free actions, but we do get requests for actions that require decisions, such as pixel interpolation being the one. Allowing the science decision to rest with the astronomer is important if they're going to trust or use the service. Maybe it's more of a comment than a question.
Yeah, I agree.
All right, we're out of time. We're running slightly late, but I think this was a good discussion and a good set of questions to have. But thank you again, Vandana, for this great talk. And let's move on to Knut.
All right, thank you very much.
While Knut is sharing his screen, let me just introduce that he's going to talk about data sets and data services at NOIRLab's Community Science and Data Center.
Okay, and do you see my my screen share?
We don't.
You don't?
Doesn't seem like it's sharing the screen.
Okay, oops, yeah, that's because I forgot to hit the share screen button. There we go. Let's see. How about now?
Yeah, perfect.
Okay, great. Thank you. Yeah, so and thanks for the opportunity to speak at this workshop, and congratulations on the 10-year anniversary to LIneA. Yeah, I'm Knut Olsen. I'm at the Community Science and Data Center at NOIRLab. So I should maybe just introduce this by describing a little bit about what NOIRLab and CSDC are. So NOIRLab is a new organization that has grown out of the former NOAO, which was Kip Peak, Ceratololo, and CSDC, the Community Science and Data Center, and has combined with the Gemini Observatory and also will include the Rubin Observatory operations, all under one umbrella organization. And the Community Science and Data Center role, since it grew out of NOAO, I think its mission is evolving as we as the NOIRLab organization continues to develop into a unified and integrated organization. And so traditionally, it has concentrated on the data sets that were generated by the 4 meters at Kip Peak and Cerro Tololo, but that role may grow as NOIRLab also evolves. To motivate why we're developing the things that we are at CSDC, I'm just going to play this movie of the imaging exposures that were that have been generated over the past 15 or so years, going back to 2004 when we first developed a public archive of our exposures. And you can see that in the early years, the first decade or so, the rate of imaging data was relatively slow. But starting in 2012, in particular with the commissioning of the dark energy camera, the images start to fill up the most of the sky through large surveys like the Dark Energy Survey, but also through community usage of our instruments. And this imaging and now spectroscopic data set as well, because we have spectroscopic surveys like DESI that are using the imaging surveys to target their spectroscopic targets. These surveys contain billions of astronomical objects, and so we need data services and archives on top of these to really make good scientific use of them. And of course, Rubin's LSST survey is going to introduce another phase change in data rate and scientific usage. And so I think this workshop, which is discussing data services and science platforms and the like, is really timely. So yeah, just to put this in graphical form, right? So at CSDC, we have an astro data archive that stores the pixel data sets, and over time, this has grown to become essentially a multi-petascale data archive of raw, reduced, and high-level derived science products from these images. And if you compare this with what we expect from Rubin, this sort of drives home the phase change that is coming with that survey. And we'll go into the hundreds of petabytes and beginning to approach the exascale that we heard talked about in high energy physics and other arenas. It's not just images, of course, or pixels. There's a variety and complexity of data here. We have photometric and spectroscopic catalogs to deal with, catalogs for both objects and unique measurements, so time series. And all of these can be served, most naturally in various ways, either through databases or files. But we also want to be able to serve the pixel data, so images in various forms and spectra are increasingly going to be common. So just a quick run through on the major DCAM surveys that we are serving through CSDC data services. These are surveys that generate catalogs, which we serve through our data services. This first one is the SMASH survey, 360 million objects here. Have surveys in the galactic plane with billions of objects and tens of billions of individual epic measurements. More recent survey release, the Delve DR1, about 500 million objects. Of course, the dark energy survey, which was the impetus for building the dark energy camera, its most recent release has close to 700 million objects. And the legacy surveys, which are the targeting surveys for the Desai spectrograph, its latest release is 1.6 billion objects. And we've also generated our own catalog. The NOIRLab source catalog just had its second data release, basically taking all the public DCAM and mosaic imaging and generating a catalog from it. This has close to 4 billion objects and almost 70 billion individual measurements. So the data volume and again complexity has grown significantly. Just to summarize the kinds of data that we are dealing with at CSDC, a lot of it is survey data from instruments like Dark Energy Camera, but it's a combination of PI-driven data sets and those from the survey teams. We also have data collections that teams deliver, such as a recent example is from the Go Green survey, a Gemini large and long program. And to put these in context, we also provide access to various public data sets like SDSS, Allwise, Unwise, Gaia, etc. And serve this data again through a combination of images and catalogs and file data products. So I'm going to just briefly go through the data services that we provide at CSDC. They're designed to enable discovery in these massive data sets, both the ones that come from surveys and so the PI-driven ones. And what we're aiming for is to integrate these into a system that provides the ability to really make scientific use out of these data sets and support the full life cycle of scientific projects from conception to analysis to publication. So the first I'll just mention is the Astro Archive. This is our petascale pixel data archive, again, mostly from the telescopes at Cerro Tololo, as well as Cerro Pachón through the SOAR telescope, and Kip Peak. Has an interface that you can make queries through a web interface or through APIs. We have a module for Astro Query to access this, as well as several Jupyter Notebook examples on using those APIs. The Astro Data Lab has been mentioned a few times already. So this is our science platform for catalog and pixel data. Provides services like queries of catalogs, cross-match of catalogs, cutouts from images from the Astro Archive and from other sources, as well as spectral access services. Users have the ability to store their own data products there, and can also publish surveys through the service. And a lot of this is enabled through a Jupyter Notebook analysis environment, in addition to the web services that are there. And then finally, I mentioned the Antares transient broker. So this is a broker that's built to handle the scale of time domain alerts from Rubin LSST. Also provides live access to ZTF public alerts. The idea here is that users can configure their own filters for winnowing down those alert streams into the events that they are interested in for their particular science cases. They can also set up watch lists for getting alerted when interesting things that pass filters happen in objects of interest, and this can also be accessed through APIs. So this is similar, I think, to a slide that Vandana showed. Basically, who are we targeting these services at? So we're targeting them mainly at researchers, both PIs and survey teams, graduate students, etc. But they're also used by various other communities. So teachers and professors in classes have used our services for education, as well as undergraduate students have used them, and high school students in educational projects, and citizen scientists in discovering new objects and things from citizen science projects. So it's a pretty diverse user base that there are various interfaces that they can use, and each of those interfaces, I think, has different popularity amongst different users. To show how these services can be used for science, just wanted to step through an example, sort of what we aspire to enable with these services. So this is an image from the Dark Energy Survey from the paper by Nora Shipp et al. Announcing the discovery of streams in the Milky Way in the Dark Energy Survey. So these are, things that have been shredded in the Milky Way halo as they're accreting onto the galaxy, and are very useful for probing things like dark matter and understanding the puzzle of galaxy formation from the point of view of our galaxy. And it shows, the Dark Energy Survey was, of course, designed to measure dark energy from extragalactic objects, but these surveys are treasure troves of discovery potential for a huge variety of science applications, this being one. And the goal of these data services that we provide is to enable the science community to make these kinds of discoveries. So in stepping through this example, I wanted to show one, how one might use the Astro archive to create an exposure depth map from the metadata that's stored in the image headers here. So this is the output of that analysis. Then use the Astro Data Lab to look for, say, dwarf galaxies and streams in the catalog data, but using the depth map to correct the density map that comes out of that. And then once having made those discoveries, you often want to look deeper in other data sets. And so one could set up then a watch list on these dwarf galaxies that are discovered in this map, and look for things that are variable or transients in the alert streams. And so here's using Antares to do that. And then once you have found something really interesting, you often want to collect more data on it. And so give a brief example of how you could then schedule a Gemini observation, assuming that you have an approved proposal with the Aeon network. That's sort of the last part. So these I won't go through in great detail on these, but basically, through a notebook of the Astro Data Archive, you can search the entire database of metadata for those images and get those images if you want. But for this, we don't do any image download at all. We just make a map of the effective exposure time through various information in the metadata, and produces this this map. And then going to the search for a halo structure in the catalog data, this is a piece of a notebook showing basically how you search for blue sources in the DES catalog data and do some star galaxy separation, and then create an aggregate map of the discoveries. And then in this notebook, one could then correct that for depth from the Astro archive generated depth map. And then we also have a notebook then here that can pull in alert events through Antares and look in those for variable objects associated with these dwarf galaxies that were detected in the catalog search. And so here we've set up a watch list in Antares, basically collecting alerts within some radius of these centers, and then finding an object here that which turns out to be an LIneA star in one of the dwarf galaxies. And then here there is through the TOM toolkit developed by Las Cumbres Observatory, can import that into another Jupyter notebook, basically access those Antares loci that were generated from the previous screen, and then schedule and monitor that follow-up observation. So this is an example of how you can use the individual services in sort of a chain to enable discovery. Now, so we're as part of NOIRLab, we're imagining that services like these could be integrated better to create a unified data center. From, if you were following this example, you could basically do all this from one login and schedule the follow-up observation, do the data analysis. So you run your science pipeline, your spectral reduction pipeline, basically on a Jupyter platform, perhaps. And then once you have your paper, publish that data again through services enabled by this data science center. And in that publication, of course, you could have digital links to your to the various stages of data products that one developed through this workflow. So this is sort of what we're aiming to develop. And of course, this will involve pulling in data from lots of different sources. So as I think Vandana mentioned, no astronomer basically stays inside the box of one data set. They want data from lots of sources. And so we want to be able to enable that kind of cross-disciplinary or cross data set interaction for astronomers, because that's the way they want to work. Of course, this is all happening in a broader context. There are lots of other data centers and science platforms. Just mention a few of them here. One of course, the most important data centers for us will be the Rubin Data Access Center. And through the in-kind program, we have a large number of independent data analysis centers that have been proposed as in-kind contributions in return for Rubin data rights. And if these are approved by the agencies, this will really provide a large multiplier of storage, computing, and data replication for Rubin users. And so I think imagining getting this network of data centers to work together, I think starts to get at the science platform network concept that Vandana laid out in the 2020 white paper that many of us were part of. And so I think this the science platform network will come to fruition in probably various ways. And I'll just end with a few thoughts, right? So NOIRLab, through its various pieces, so the Rubin operations, Gemini, the telescopes at Tololo and Kepik and Sarapachelem, really provides an opportunity for us to build an integrated data science center for our ground-based community. And it's not the only data science center like this, but we want this to be an integrated system. We know that we need to strengthen the links between our own data and services internally, including the links from proposing to capturing data to reducing data, comparing with other data sets, and doing the analysis and publication and follow-up. We'd like this to be an integrated and unified system. We know that we can't do everything under one roof, and so having a functional network of data centers and science platforms, I think, is important. I think this will depend on many of the key common technologies that have been mentioned so far at this workshop, including deployments to the cloud, data lakes, VO protocols, use of containers broadly. And I'll just mention in particular Jupyter technology is of course a popular interface now, and I think is the kinds of things that you can do in a Jupyter notebook are only going to grow in popularity. And from the point of view of the users, they just want all their data to be available from within that notebook environment, and then they can install their own software. They have lots of software pre-installed. They kind of don't care about all the underlying stuff. That's the things that the data centers had to enable. They just want it all to be there in one place. Now I mentioned that on Archive tonight, there's a paper from Stephanie Juno about the various, about a couple of examples of using Jupyter in science platforms that was delivered, grew out of a talk at the JupyterCon this last year. So that's all I have, and happy to take questions.
Thank you, Knut. We do have a couple of questions for you. There's one by Mubdi Rahman. So the notebooks are fantastic to explore prototypes and analyses, but oftentimes they're the first stage of a larger production analysis that would likely not be efficient in a notebook environment. Does NOIRLab have plans to support turning notebooks on your platform into something more production ready?
Yes. So it's definitely on in the plans. We had it was part of the vision for Astro Data Lab that we developed several years ago now, was to be able to do that, to take the sort of the workflows developed through notebooks and turn them into production computations. And we're right now working on our 5-year plan for NOIRLab, and that kind of capability is certainly going to be important as part of that.
And another question, as archives begin to offer these kinds of remote data analysis capabilities, what do you project for your computational needs as larger data sets begin to dominate? Will at some point there be a cycles crunch where it's technically possible to work next to the data, but there's not enough computing for everyone to do it?
Yeah, it's a good question, and I think the right, you can maybe look at the Rubin sort of model for this, where the computation that is set aside for users at the Rubin Data Access Center is like 10%, I think, of the data production capacity, and it's been a concern from users, I think, from fairly early on that it might not be sufficient for what they want to do. I think the opportunity from the Rubin IDAC program is really important here, as if you look at just the number of computing cycles and storage that network would provide is, several times what would be available to them just at the Rubin Data Access Center. The challenge, of course, is going to be connecting those resources to the use cases in an efficient way, and I think that is work cut out for us as we go through. And so I think this concept of a data lake where people could put data and then bring their own resources to bear on it, I think is a really good one. It'd be great if we can make that work. But I think we'll have to proceed as practically as possible and taking advantage of the computing resources that are out there. I'm not sure if I've really answered the question, but at least I think we have a lot of compute out there. It's just bringing it in an efficient way to the problems that we need to make sure that we're able to do.
All right, thank you, Knut. This is all the time we have for today. Thank you all the speakers again for a wonderful set of talks and a really nice conversation afterwards. One of the things I'd like to remind everyone is that we start again tomorrow at 11:50 Brazilian time, and we'll have a roundtable at the end of the day tomorrow. The topics or the questions for that roundtable are being proposed by you, by all the attendees and participants. Please do so if you have an idea, something that you want us to discuss, by posting a message to the discussions channel on the Slack. Let me hand it back over to Lise for any final words.
Well, I have none. So thank you very much to all the speakers. It was a great day again. And I'll see you tomorrow at 11:15. Thank you. Okay, Rodrigo.